I'm going to look at some basic integration techniques. So in this video, what I want to look at is how we can essentially rewrite any kind of integral given and then just be able to solve it using perhaps something like u substitution, or even, just rewriting it so that it's actually a lot simpler to, use our conventional methods of integration. So one of the first methods is called expansion, or we could just say that, one of the things that we need to do as it relates to an integral is to expand it. What do we mean by that? We mean that if we have something like e to the x, and let's say that it's plus 1, but it's squared dx, well, if we expand it as the integral e to the 2x plus 2e to the 2x, this is actually going to give us plus 1, and then we have that now it's a lot simpler to integrate this. So this is one of those techniques that we can apply as needed as it relates to, how do we solve something like this. So another one is that we can actually separate. Okay, now we actually have seen this demonstrated a few times, but like we can look at one where we have something like the integral of x plus 1 divided by x squared plus 1 dx. Well, by separation, we mean that we can rewrite it as the integral of x divided by x squared plus 1. And then we could put dx, for instance, and then put plus the integral of 1 over x squared plus 1, and then we have dx. Now we have that this can be solved by u sub, and now this is actually just going to be the arctangent function. So that's one thing that we can do in terms of separation. But another method that we do look at, or another technique, is where we complete the square. So if we complete the square, basically what that means is that we're going to rewrite it by saying, like if for example we have the integral of 1 divided by the square root of 2x minus x squared dx. If I rewrite it by completing the square as 1 over the square root of 1 minus the integral of x minus 1 squared, well, now this is actually just u sub. But it's also looking at arc sine in either case for the integration. Now, another method that we can use, for example, is what is known as long division. So we can also use long division as another way of integration. So what do we mean by this? Well, we mean that if we have, let's say for example, the integral of x squared divided by x squared plus 1, and then that's dx, well, you can rewrite this as 1 minus 1 over x squared plus 1, and then you have dx. Now this is a lot simpler, so this is long division. Okay, so we have that long division may be applied, and then once we get from there, then you can kind of see that if you wanted to solve this, this is just x minus arctangent inverse of x plus c. And then that would be it with regard to the solution. So it started off as, x squared over x squared plus 1, and in any case, that's not too bad. But we also have another form of that we have for integration, which is add and subtract. Okay, but what does that even mean, add and subtract? Okay, now add and subtract means, like for example, like if I have the integral of 2x divided by x squared plus 2x plus 1, and then this is dx. Well, one thing that I notice is that if I were to subtract 2 or add 2, because notice that if you use u substitution, you would end up with u is x squared plus 2x plus 1, but du is 2x plus 2. So that means that I need a 2 there. How do I do that? I add 2 and subtract 2. So we rewrite that as the integral of 2x plus 2 divided by x squared plus 2x plus 1. And then, let's see. Oh, well, we could put parentheses. Minus 2 over x squared plus 2x, actually, right? 2x plus 1, and then that's dx. And then we'll just close it. Now, notice that in this case, u substitution actually will be very useful, because then you can just rewrite this as the integral of 2 divided by x plus 1, and then you rewrite this as minus 2 divided by x plus 1 to the second power. And then now this is actually a whole lot easier in terms of like integrating this equation. Now that's not the only way that we have to do it, for example. I mean, yeah, there's actually many different things that we could do with this. But, you know, at the moment, we're not going to try to use any advanced techniques that go beyond the scope of the course, essentially. So, another thing that we can do is actually look at some identities. Now, actually, I have it in my notes that I did solve this, actually. If you would like a solution, that would be 2, the natural log of the absolute value of x plus 1, minus, actually it's plus, right? 2 over x plus 1, and then plus c. So this would be the solution for this particular integral in either case. Okay, now the other that you might need to use, another technique of integration, is looking at what is known as trig identities. Okay, so trig identities, those are the ones of which that you would have learned in trigonometry or pre-cal, such as like let's say cosine squared x plus sine squared x equals to 1, tangent squared x plus 1 equals to secant squared x, and then 1 plus cotangent squared x equals to cosecant squared x. Now you might wonder, okay, well, how exactly does that help me in terms of integrating a function? Well, think of it like this, for example, like let's say that you have 1 over 1 minus cosine, for example. Okay, so we have our identities, and our question may be, what if we were integrating 1 over 1 minus cosine of theta d theta? Well, in this case, we need to rewrite this, right? So how do you rewrite this? Well, you have to rewrite it by multiplying by the conjugate of the denominator, which in this case is 1 plus cosine theta. Once I do that, I end up with 1 minus cosine theta, actually it's a plus, isn't it? Divided by 1 minus cosine squared theta. But accordingly, the denominator, this is actually sine squared x. Okay. So what that does is it tells us that we now have 1 over sine squared x, and then we have plus cosine of x divided by sine squared x. Now, in actuality, though, we could probably, say that, well, isn't this cosine squared x? And then we could probably rewrite this as cotangent cosecant plus cotangent of x, and then cosecant of x. And then remember that we were actually integrating this, so we were integrating that, and that's dx, but, that's going to be negative cotangent of x minus cosecant of x, and then plus c. Okay, so we have that this would be the solution for that particular type of question, right? Now, in some cases, though, we can look at some other techniques of integration and see, which does this fall under, for example. But, these are the core ones in either case, like, for basic integration techniques. So, what if we were to look at an example where we have that we have a definite integral, right? Okay, so let's say that we have an integral from 1 to 3 of 2 divided by x squared plus 2x plus 1, and this is dx. Well, I know that basically the denominator, it has to be rewritten. Okay, so we can rewrite the denominator as 2 over x plus 1 to the second power, and this is going to be dx. But what would you do to solve this? You would say that that's going to be u equals to x plus 1, and du equals to dx. So what does that tell you? This tells you that you have the integral of 2 divided by u squared du, and basically you have that if, for example, x is equal to 1, what is u equal to? Well, it's equal to 2. If x is equal to 3, what is u equal to? Well, it's equal to 4. So that means that this limit is going to be 2, and this is going to be 4. Okay, but how do I solve this? This becomes 2u to the negative 2 plus 1 divided by negative 2 plus 1, and this is from 2 to 4. Okay, but that gives me the following. It gives me negative 2 over u from 2 to 4, and then evaluating this using the fundamental theorem of calculus that says, you take f of b minus f of a. That's going to be minus 2 over 4 plus 2 over 2, which is actually just equal to 1/2. So the answer is 1/2. And that was by u substitution. Okay, but let's say that, maybe it wasn't so clear how we can apply a u substitution, because in some cases we may need to just rewrite it totally, right? So, okay, well, what if we had 1 plus e to the x dx? Well, here I don't have what is, a convenient part of this where, like, I say that u is equal to e to the x, because you have that when you do this, you get that there's an extra e to the x that's not there, for example. So, okay, well, what we can do with this is say, well, why don't we just multiply the whole thing by e to the negative x? So in doing that, we have the integral of e to the negative x divided by e to the negative x plus 1, and then that's dx. So this tells us that u equals to e to the negative x plus 1, and du is equal to negative e to the negative x dx, which this is going to be equal to the integral of minus 1 over u du. Okay, now in integrating this, you end up with minus natural log of the absolute value of u plus c. But in any case, what was u, right? U, for this one was e to the minus x plus 1. Okay, well, in either case, we can actually plug that in if we want to. Yeah, so one thing though that I'm going to write out is that u equals to 1 plus 1 over e to the x, meaning that this is the same thing as e to the x plus 1 over e to the x. Okay, keep that in mind. Minus the natural log of the absolute value of e to the x plus 1 over e to the x plus c. Okay, but now this actually becomes, because of the negative sign, it becomes the natural log of the absolute value of e to the x divided by e to the x plus 1 and then plus c. Okay, but this can be rewritten even further as the natural log of e to the x minus the natural log of e to the x plus 1 plus c, and this equals to x minus the natural log of e to the, okay, sorry. So that's e to the x plus 1 and then plus c. Okay, so we have that our solution is this right here. Okay, so this is our solution for the function, or the antiderivative of 1 over 1 plus e to the x. Okay, so note that if you differentiate this, that you will find the exact same thing in either case. Now, suppose that you wanted to look at, for example, just another where you have a definite integral, perhaps. Okay, well, another type of example would be like if you have the integral from 0 to 9 of 1 divided by, let's say, like 4. Okay, so like, let's say that you have 4, and then you have 1 plus the square root of x. But let's say that there's another term that's, the square root of x. So out there, and then we'll just put dx. Okay, so just extend that. Now here, u is going to be 1 plus the square root of x, so du is going to be 1 over 2 root x dx. Now notice that if I divide by 2, that'll give me 1 over 4 root x dx, which is exactly what I needed. So in this case, we have that this becomes the integral of, okay, well, if you plug in 0, you get 1. If you plug in 9, you get 4. And this is going to be 1 over the square root of u, and then that's du. But there was a 2 there, right? So yeah, that's a 2, and then that's du. But notice that that's going to be the square root of u from 1 to 4, which means that this would be the square root of 4 minus the square root of 1, which in this case is 2 minus 1, which gives you 1. So the solution is just 1, actually, in either case. Now, you have that in some cases, definitely you may need to complete the square, right? So what I want to conclude with is just looking at an example where, we need to complete the square. So let's say that so what we can look at here is the following. Let's say that we're integrating 1 divided by x squared minus 4x plus 13, and all of this is going to be, just an indefinite integral, right? Now, to complete the square, we need to take x squared minus 4x plus 13. We need to basically say x squared minus 4x plus half of negative 2. So that's going to be, well, yeah, it's negative 2 when you take half of negative 4 and then you square it. But we're going to take 13 and we're going to subtract the same thing. Okay, so this gives us x squared minus 4x plus 4 plus, well, 13 minus 4, which is actually just going to be x minus 2 to the second power, and then plus 9, right? Okay, so that tells us that our integral becomes the integral of 1 over x minus 2 squared plus 3 squared. Okay, now the only thing though is that what we can do with this is probably use that if we say u, so if we say another substitution or just a substitution here, what we're going to say is that u, and yeah, let's put the dx, right? Okay, dx. Let's say that u is equal to x minus 2, though. So du equals to dx. Okay, but what does that do for the integral? It changes it to 1 over u squared plus 3 squared, and that's du. However, we now know that when we rewrite it like this, that essentially you're just going to use that the antiderivative of something like this, of this form, would be 1 over a arctangent inverse of u over a, and then plus c. So in this case, this would be 1 over 3 tangent inverse of u over 3, and then we have that would be plus c. Okay, so in this sense, we do have our answer because we just need to change it, right? So we'll go ahead and change it by using 1/3 tangent inverse of x minus 2 over 3 and then plus c. So this would be our solution for the integral of 1 divided by x squared minus 4x plus 13. Now, you can probably, for example, try a different integral if you wanted to. Like if you wanted to integrate this from supposedly, maybe from 2, and then maybe you put that it's going to be up to 5. Then in that case, what you would have is that, this would actually be equivalent after you do the integration, obviously. This would be equivalent to pi over 12, actually. And you can look at that later, what if you were integrating from 2 to 5, what would that look like? And the answer would be pi over 12, actually. But in any case, if you want to try another type of example, then you're more than welcome to, where you try to complete the square, for example. So if you have, let's say, yeah, so suppose that you had the integral of positive 3 over, let's say, the square root of 21, and then you had minus 9x squared minus 12x. Okay, and we have to extend that a little bit. Okay, so what you would need to do is to try to recognize, okay, well, what can we do with this, right? Well, from here, you have negative 9x squared minus 12x and then plus 21. So you could probably take out a minus 3. Let me see. Well, you could probably take out a minus sign where you have 9x squared minus 12x. And then from there, let's see. Yeah, actually, so the goal is to basically rewrite this in terms of a perfect square, right? Okay, so when you do this, that's going to be plus 21. So essentially, yeah, essentially we just have to rewrite this as a perfect square and just figure out how to make this a perfect square. So essentially we want to get that, right, to be perfect square. So take half of this equation and let's see, what can we add? Well, if we add plus 2 squared, then that would be 4, right? So that would be, but it would be minus, wouldn't it? But we already took it out, actually. Yeah, actually it would be plus 4. Okay, got it. So minus 4 and then plus 1, or plus 4. So then that would be minus times 3x plus 2 squared, and then you would have that would be plus 25. Okay, so in this case, this would be our perfect square in either case. So now you have that the integral will now become the integral of 3 divided by the square root of 25, and then we have minus 3x plus 2 to the second power, and then this would be dx. Okay, so now what you would need to do from here, and you know, if you wanted to just do it easily, where you just said that you just subtract 4 and add 4, that's actually a lot better, and that's actually what I was doing kind of when I was thinking of how do we make this into a perfect square in either case. And the only way that I could think of it was to force the 21 to be a square number, which is 25. So then that's how I was like, okay, well, I'm going to have minus 4 and then plus 4, and so on. So that's kind of like how I fixed it in a way. So once you get up to this point, you say that u is equal to 3x plus 2. Now, if you do that, then that means that du is 3. Let's do this. 3 dx, which, what does that mean for your integral? That means that you end up with 1 over the square root of 25 minus u squared du. Now, the only thing, though, is that once you get up to this point, you're going to have to use that this would be actually inverse sine. So you would have to use that this is going to be inverse sine, because you have that this pretty much tells you that when you're integrating something like where you have the 5 squared and then you have the u squared, it's essentially going to be where you take the variable, the u, over the a, and then it would be plus c. Okay, so essentially we have our answer, but it's in terms of u and a. So I'll just leave it to you to be able to figure out something like this. And then, you know, it would be interesting, for example, like if you were going to evaluate this, say, for example, from 0 to 1. Like if you were going to evaluate this from 0 yeah, from 0 to 1, and then like see like what would that come out to in terms of like the answer for this one. So that's going to be it, and I hope that this helps and that, you know, it opens you up to, you know, seeing integrals from a different perspective, and that in a sense it's going to require what is thought of as ingenuity, but more creativity, if anything.